Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Electrodeposition and Electroless deposition technique from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, electrodeposition technique is described and the various factors that influence the electrodeposition process are discussed. Further in this module, mechanism of electroless deposition involving a metal with valency Z is studied. Further, a comparison of electrodeposition and electroless deposition is presented in this module. Also, various applications of electrodeposition and electroless deposition are discussed. Electrodeposition technique is a very old process which involves coating a thin layer of one metal on the top of a different metal to alter its surface properties by donating electrons to the ions in a solution. This bottom-up approach is versatile and it can be applied to a wide variety of potential applications. Electrodeposition has gained much interest in recent past owing to its capability to fabricate one-dimensional structures such as nanorods, nanowires, and nanotubes. Electroplating is another technique which is analogous to the electrodeposition. Apart from producing metal coatings, this technique is also used in electrometallurgy, wherein a metal is extracted from its ore. Its another use includes formation of molds to create objects in the final shape. This process is called electroformation. Most of the metal depositions produced by this technique are crystalline. And for this reason, this technique is also termed as electrocrystallization. This term was first used by V. Kitavosky, a Russian chemist in the early 20th century. Owing to the presence of positive as well as negatively charged ions, electrolyte conducts ions. The electrolyte is prepared by dissolving the salt of the desired metal to be deposited in a suitable solvent, that is, most commonly in water. The solvent can also be an organic or ionic solid for specifying electroplating process. For electrodeposition, the working electrode or the cathode and the anode or the counter electrode are immersed into the electrolyte contained in a vessel or cell. To flow electric current in the circuit, a battery is usually connected to the electrodes such that cathode is connected to the negative terminal and the anode is connected to the positive terminal of the battery. It is usually utilized to deposit a coating, mostly metallic, onto a surface through reduction at cathode. Substrate to be coated works as cathode immersed in the solution consisting salt of the metal required to deposit. The metal ions get attracted towards cathode where they are reduced to the metallic form. Electrodeposition can be considered as a type of conventional thin film deposition technique called electrolytic deposition, and electric current is used to reduce the cations of a selective material from an electrolyte and deposit on a conductive surface. It is often performed to make selective electrical and corrosion resistance of a material or to enhance heat tolerance, decrease wear and friction. Figure 1 shows the schematics of the electrode deposition process for nickel chloride solution. The electrolyte solution possesses the positively charged nickel ions or cations along with the negatively charged chloride ions or the anions. When an external field is applied to the system, cations migrate to the cathode and deposit as metallic nickel after reduction. So, nickel 2 plus 2 electrons will give the metallic nickel. Simultaneously, to maintain the neutrality of electrolyte, nickel from anode gets dissolved in the solution. So, nickel gives nickel 2 plus 2 electrons. This phenomena is termed as electrolysis. Usually, a platinum mesh acts as anode. Oxidation of water occurs at the anode. That is, 2H2O gives 4H plus O2 plus 4 electrons. The quantity of chloride ions is unchanged during electrolysis, but the content of nickel 2 plus ions will decrease while concentration of H plus ions increases with time. Due to the effect of applied voltage, reorganization of ions takes place near the surface of electrode and it leads to deposition of an Helmholtz double layer, which is an electrical double layer succeeded by the creation of diffusion layer as shown in figure 1b. This process can be summarized as first is migration, that is, hydrated metal ions move towards cathode due to the impact of current as well as by diffusion and convection. Secondly, the electron transfer, that is, at the surface of cathode, hydrated metal ions enter the diffuse double layer where water molecules of hydrated ions are aligned. Afterwards, metal ions reach Helmholtz double layer wherein their hydrate envelope is removed. The dehydrated ions are adsorbed at the surface of cathode after neutralization. The adsorbed atoms then migrate or diffuse to the nucleation point on cathode surface. Thickness of electroplated layer at substrate can be controlled by plating time duration. By some modification in electrode and the electrolyte solution, this method can be successfully used for fabrication of nanomaterials, nanorods, and porous structures. Factors that influence the electrodeposition process are: first one is the current density. Secondly, the nature of the anions and cations that are present in the solution. Third is the composition as well as the temperature of the bath. Next is the concentration of the solution. Then the waveform of the supplied current. Also, the presence of impurities strongly influence the electrodeposition process. Physical as well as chemical nature of the surface of substrate is a major factor which influences the electrodeposition process. Let us now discuss some applications. First one is the decorations, where an expensive metal is coated over the surface of a base metal to enhance its appearance. Typical applications include jewelry, furniture fittings, tableware, etc. Another important application is that in protection. Corrosion resistance coatings include chromium plating of automobile parts as well as appliances for domestic use, such as nuts, screws, as well as electrical components. Then electroforming is another important application that includes producing molds, sieves, screens, dry shaver heads, record stamps, dies, etc. Enhancement is also an important application as it involves improving the electrical and thermal conductivities, that is solderability, reflectivity, printed circuitry, and electrical contacts, production of microparts for MEMS, etc. In brief, charge transfer mechanism is at the heart of the technique. Metal ions are reduced to metal chosen to deposit by the chemical reducing agents. The coating material is provided by metal salts instead of anode. Refilling is done by addition of either salt or external loop to the anode of a metal, which has better efficiency than cathode. For reducing the metal, a substrate is used, which works as cathode, and the reducing agent provides the electrons for completing the process. In this technique, experimental process takes place only on catalytic surface, and if reaction conditions are not correct, then it can cause the reaction in whole solution that may provide undesirable results. Figure 2 shows the deposition process in electroless plating along with the half reactions of the cell for a metal having Z valency. The metal ions are reduced by the electrons provided by the reducing agent. The produced metal atoms are deposited on the substrate. The most important characteristic feature of electroless plating is that it can also be used to metallize or deposit metal, semiconductors, as well as insulators. For example, plastics, glasses, and ceramics. The mechanism of electroless deposition involving a metal with valency Z is shown in the figure. In electroless or autocatalytic plating, the metal ions are reduced to form metals in the presence of specific catalyst. Thus, selected surfaces can be coated with the desired metal layer by depositing catalyst. The electroless plating bath for nickel consists of firstly a nickel source, that is nickel sulfate, that is NiSO4H2O6, or nickel chloride, NiCl2.6H2. Then a reducing agent is required, such as sodium hypophosphite, that is NaH2PO2.H2. A buffer is required, such as triammonium citrate, that is NH43C6H5O7. In addition to these components, ammonium hydroxide, that is NH4OH, is added in small quantities to increase the bath pH. pH determines the bath stability and uniform deposition rates. Typically, pH is kept somewhere between 8 and 10. Electroless plating from nickel sulfate bath undergoes the following reaction. NiSO4 plus NaH2PO2 plus water will give nickel plating plus NaHPO3 plus H2SO4. Let us now study the electroless deposition method. It is the deposition of solid continuous coatings or films, that is powder of metals, alloy or compound from an aqueous or non-aqueous solution or melt without any external bias. Thus, electroless deposition is purely a chemical process which involves oxido-reduction reactions. Coatings which are produced by this process are uniform, and also they are continuous, which makes it an attractive technique for various purposes including electronics, energy conversion, wear-resistant coatings, biomedical, aerospace, as well as automotive industries. This technique can be used for deposition of metals, alloys, salts, oxides, polymers, etc. While metallic electrodeposition, including reducing the metallic ions, has always been cathodic reaction, deposition of the metal oxides is an anodic process due to oxidation of metals. Therefore, in electroless deposition of the metals, reducing agents are required, and for depositing compounds, oxidizing agents are necessary. Let us next discuss the advantages of electroless deposition. If the motive is only to improve corrosion resistance rather than the beautification as applicable to jewelry industry, electroless plating is generally preferred because, because it results in more hard and less porous plated parts. Therefore, electroless plated components are more resistant to corrosion. Thus, electroless plating is more popular in industries where parts are vulnerable to wear and corrosion, such as oil fields or marine applications. Electroless plating is also preferred on parts like pumps and valves, which are frequently subjected to corrosive agents during their operating life. Let us next discuss about the comparison between electrodeposition and electroless deposition technique. The comparative schematic of both electro and electroless deposition techniques has been included in Figure 3. The fundamental distinction between the two methods is the use or not of electricity. Electroplating makes use of a power source like a battery or rectifier, which delivers electricity to a component in a chemical solution, altering the chemical composition and depositing a hard durable metal coating onto the surface of component. Both the techniques make component tougher and more corrosion resistant. Both techniques can also make a part more attractive, although this is usually only an issue when plating jewelry or other parts that consumers are likely to view directly as opposed to parts that you are more likely to situate within a larger machine or use on a factory floor. Electroplating is a more complex process than electroless plating. It requires clean conditions. It uses potentially hazardous equipment, and in some cases it requires multiple applications to get the desired plating thickness. Electroless plating is a much less complex process. In electroless plating, we start by cleaning the component with chemical cleansers that remove oils and other corrosive elements. Then dip it in aqueous solution and add anti-oxidation chemicals. The result is a plated component that is highly resistant to friction and corrosion. Also, with electroless nickel plating, there is no complex filtration or other equipment required, and since there is no electricity, there is also no danger of electricity related accidents. Electroless deposition also results in highly uniform metal deposits having consistent thickness all around the part. Therefore, parts with complex shapes where uniform plating might be difficult to achieve using conventional electroplating methods, electroless plating may be a much better alternative. Electroless plating is a versatile technique to produce a broad range of coatings. Most popular industrial coatings include low phosphorus, which is hard. This bath is used to deposit coatings having hardness around 60 Rockwells. The additional advantage of this technique is that it provides a uniform all-round coating of complex features. Owing to high uniformity of the deposition, there is no need for post-treatments such as grinding. Electroless low phosphorus nickel plating provides superior corrosion resistance towards alkaline conditions. Its another application is medium phosphorus, which is of bright high speed. Medium phosphorus electroless nickel plated steel parts give performance similar to stainless steel. There is no buildup of electroless nickel on edges or ends, and it covers both inside and outside uniformly. The hardness can be increased from 45 to 68 Rockwell C by applying some sort of heat treatment. High phosphorus. High phosphorus coatings provide maximum resistance towards corrosion, and it is industry standard where strong acid conditions are frequent. Example, oil drilling, coal mining, etc. However, these coatings suffer from poor solderability as they are only solderable for a brief time. Nonetheless, this property makes them particularly desirable for electronics parts including connector housings and semiconductor packaging. Electroless nickel or Teflon composite now. This is the recent application area of electroless nickel plating technique. Teflon coating yields a very low interfacial friction. In this technique, microscopic beads of Teflon are co-deposited up to 20% along with the electroless nickel. This coating is highly desirable for solving problems like sticking, galling, or dragging with moving parts or heated sealed surfaces. This can be a better alternative to liquid lubricants in some applications. Another application is that of electroless nickel on zinc die-cast. In applications which require corrosion resistance along with the resistance to chipping and flaking, electroless nickel deposition on zinc die cast is highly desirable as it circumvents the need for copper layer. Now we will discuss some applications which are more suited for electroless deposition. Electroless depositions find applications in industries where parts have complex shapes or may be subjected to heavy corrosive factors. They are prime candidates for electroless plating. These industries may include food service industry, for example, malts and food processing machine parts. Then oil and gas industry, which includes anything from valves, balls and plugs to barrels, pipe fittings and more. Then the automotive industry, it includes vital car parts like shock absorbers, cylinders, brake pistons and gears. Then the aerospace industry, it includes valves, pistons, pumps, rocket components, etc. In the chemical industry, there includes pumps, mixing blades, heat exchangers, filter units, etc. Plastics and textiles includes molds, dyes, machine parts, spinnerets, extruders, and so on. So students, let us summarize what we have learned in this module. In this module, electrodeposition technique was described and the various factors that influence the electrodeposition process were discussed. Then, the mechanism of electroless deposition involving a metal with valency Z was studied in this module. A comparison of electrodeposition and electroless deposition was also presented here. Finally, the various applications of electrodeposition and electroless deposition were discussed. Thank you students for your attention.